Okay, so to graph these, we're going to start out with our standard XY coordinate plane. The first one. Now, the first thing we need to do is locate the translations in the origin, the shifts in the origin. Remember, our graph kind of goes around the origin with the x-axis, y equals 0, is that horizontal asymptote. Well, some of the things that get done here move that horizontal asymptote. This number here, for example, the +1, moves my horizontal asymptote up to +1 instead of y equals 0. The x minus 3, remember we go the opposite direction. Oops, go ahead. Oops, sorry, thought there was a question there. So we move over where the y-axis is, the behavior at the y-axis moves over, and we now have that behavior at x equals 3. So that's from the x minus 3. This is 2 to the power of x, so it's going to be a curve that looks something like this. Normally, it always goes through 1 unit above where that vertical axis would be. But because this is -3 times it, it flips it over. We're going to be under the horizontal asymptote, and the 3 means instead of 1 unit below, it's going to go past 3 units below where that horizontal axis would be. It's going to look something like this. So that's the first one. The second one, the +2 means our horizontal asymptote moves up to y equals 2 instead of y equals 0. X +2, we move the opposite direction, so that means the behavior that would normally be at the vertical axis is over at x equals -2. +2 means instead of going through 1 unit above the asymptote, it goes through 2 units above the asymptote. Our behavior, our graph looks something like that. Number 3, since this value in here, this little a value, is between 0 and 1, that means the curve goes the opposite direction, like this. Now the -2 means the horizontal asymptote, instead of being at y equals 0 at the x-axis, is going to be at y equals -2. The x minus 1, we move over +1. The behavior that's normally at the vertical axis is now going to be at +1. Normally we would go through that 1 unit above the asymptote, but the 3 says we go through it 3 units above the asymptote. And because, again, that's a is between 0 and 1, the curve looks like that. Finally, the last one. -1, of course, that means our horizontal asymptote is going to be at y equals -1, 1 unit below the x-axis. X +2, remember, it goes the opposite direction, so that means our normal behavior for the vertical axis is going to be moved over to x equals -2. The 2, instead of going through 1 unit above the horizontal asymptote, means we go through 2 units above the horizontal asymptote. The 1/4, of course, means it is curving down instead of up. Oops. Got to get to my asymptote. It's going to look something like that in red there. Any questions on the graph? Okay. Solving these equations. I'm going to start out with the 25 to the power of 3x minus 1 equals 3125 dx plus 7. As we look at these, I kind of did these in reverse order, did the most difficult ones first. What we need to do is we need to find a common base for that exponent. Both of these can be broken down as powers of 5. 25 can be written as 5 squared. So that'll still be 5 squared then to the power of 3x minus 1. 3,125 is actually 5 to the 5th power. So that'll be 5 to the 5th power to the power of x plus 7. Now we need to use our powers or properties of exponents to combine those powers. 5 squared to the power of 3x minus 1. Remember, when we have a power of a power, we multiply the powers. We're basically distributing the 2 through the 3x minus 1. Gives us 6x minus 2. On the other side, the power of 5 and the power of x plus 7 get multiplied, so we're going to distribute the 5 through the x plus 7, giving us 5 to the power of 5x plus 35. Now I'm going to pause there. Anybody have any questions on where this equation here came from? Okay, so now that we have the same base on our exponent, we know that the powers have to be equal. 6x minus 2 has to equal 5x plus 35. Now we have a linear equation we can solve. We can combine anything that we can combine on either side. Right now there's nothing to combine on either side. Make sure the variable is on one side. Well, it's on both sides right now, so we'll get rid of the smaller one. Subtracting the 5x. 6x minus 5x is 1x, or just x. We still have the minus 2 over there. Equals 35. Last step to solve the equation is just going to be to add the 2. X equals 37. Any questions on that one? Okay, so let's go up to the next one. 4 to the 3x minus 7 equals 32 to the 2x. This is actually an example I believe I used in class on Monday. So again, both the 4 and the 32 can be written as powers of 2. 4 is 2 squared. That's still going to be to the power of 3x minus 7. 32 is 2 to the 5th, still to the power of 2x. Again, we need to combine the powers. A power of a power, or the power of an exponent, we multiply the powers. So 2 times 3x minus 7, we have to distribute that 2. So that's 2 to the power of 6x minus 14. 2 to the 5th to the power of 2x. Again, we multiply the 5 and the 2x. 5 times 2x is 10x. Once again, we have those as exponents with the same base, so we know the powers have to be equal. So the 2's are going to come out of play. We know 6x minus 14 equals 10x. And from here, we're just solving a linear equation. We combine what we can on either side. There's nothing to combine here. The variable is on both sides though, so that's the next thing we need to do is get the variable on the same side. So we'll subtract the 6x. We have negative 14 equals 10 minus 6 is 4x. Now we can solve. Our only step to solve is to divide by 4. So negative 14 divided by 4 is a negative 3.5 equals x. Any questions on that one? Okay, our next one, 8 to the x equals 32. Well, again, we still need to write these as exponents with the same base. 8 is 2 to the power of 3. That's still the power of x. 32 is 2 to the power of 5. So 2 to the third to the power of x. I multiply the exponents. Multiply the powers. 3 times x is 3x equals 2 to the fifth. So from that, we see that the equations, the powers have to be equal. Again, we got the same base. So 3x equals 5. All we have to do to solve that is divide by 3. X equals 5/3 or 1 2/3 if you prefer it that way. Our last one. I saved the easiest one for last. Three to the 5x minus 5 equals 243. I still have to get this. I shouldn't say the easiest. This one's a little tricky. I still have to get these as exponents with the same base. So the 3 to the 5x minus 5 isn't going to change. 243, however, is 3 to the power of 5. Now they have the same base. We set the exponents equal. 5x minus 5 equals 5. A lot of 5s there. We can nothing to simplify on either side. The variable's already on one side, so we'll start to solve. Add 5, get rid of the minus 5. 5x equals 10. And we'll divide by 5. X equals 2. Any questions there? Okay. So of course, that's the solving and graphing part. We also talked about the exponential growth and exponential decay. Those are examples that we will come back to in the next couple of classes as we get into solving these equations and strategies for solving these equations. Today, all we were able to do was turn them into the same base. Like this one, both of them had to become 2 to the power of something so that we can set the exponents equal to each other. But what if one of them is not an exponent? I'm getting some feedback from somebody. Carter, I think it might be you. Do you want to try to mute your microphone, please, and see if that helps?
Yep.
Okay. I think that's it. That sounds a lot better. Thank you. Okay, so today we're looking at the other side. Remember, we talked about all the operations in math come in pairs. They're inverses. You know, we have the obvious ones, addition and subtraction. If you add a number and then you subtract that same number, you get right back to where you started from. Or the other way around, if you subtract a number and then add it, you get right back to where you started. Multiplication and division are the obvious ones. You multiply by a number, divide by that same number, you're right back to where you started. A little less obvious, but still just as important and just as much inverses, are powers and roots. If I take a number like 3 to the power of 5, I get 243. If I want to get back to the 3, I use a fifth root. Now, just like all of our other inverses, this fifth root is defined in terms of the main operation. A root is a kind of a byproduct of that main operation of an exponent. So the definition of a root like this is asking what number to the power of 5 is 243. If you recall when we briefly talked about integers, the definition of division. If I say 24 divided by 6 equals what number? What that's asking me is 6 times what number, or what number times 6, probably more specifically, equals 24. It's a related multiplication problem. And the same with addition. If I say 7 minus 2 equals what number, what I'm saying is what number plus 2 equals 7. So they can be turned into their inverse operation. When we're looking at exponentials, we have that same power. If I have 3 to the power of x equals 81. To solve that, the inverse operation of an exponential this is called an exponential, if you don't recall, is a logarithm. So the logarithm, first of all, has to take account the base of the exponent. When we were doing powers and roots, remember it was the power that defined the base of our radical, the base of our root. Something to the power of 5 gave us a fifth root. Here it's not the power that we're trying to get rid of, it's the base of the exponent that we're trying to get rid of. So whatever the base of the exponent is, has to be the base of our logarithm. So this is going to be a log base 3, because the base of our exponent is a 3. And so what we're going to be saying here is the log base 3 of 81 equals x. These two statements here are equivalent. They're saying the same thing, just like these two are equivalent. Saying the fifth root of 243 equals question mark. Well, question mark to the power of 5 equals 243. They're equivalent problems. So that's one of the first things we need to be able to do with these logarithms is to convert them to their equivalent exponential form. So if we have log base b of x equals y, that is saying b to the power of y equals x. So if I want to solve some basic logarithms, I use that conversion. Log base 5 of what number is, oops, actually I should do this. Log base 5 of 125 is x. I convert it to that exponential form. This is saying 5 to the power of x equals 125. Well, I know 5 to the third power equals 125, so I know x equals 3. Let's practice here a little bit converting from logarithmic to exponential and exponential to logarithmic. So if I have log base 2 of x equals 8. To find the equivalent exponential form, the base of the log is always the base of my exponent. The solution of the log is always the power of that exponential. Then the object of my log is always the result of that exponential. So log base 2 of x equals 8 is equivalent to saying 2 to the power of 8 equals x. So if I have log base x of 729 equals 3. Actually, okay, let's do 6 equals 6. The equivalent exponential form, x, again, the base of the log is the base of the exponent. The power of 6, the solution is the power, equals the object of the log is the solution of the exponential. So in your notes, I want you to convert these two. Log base 7 of x equals 3. Log base 4 of 256 equals x. And log base x of 115,625 equals 6. Convert those into their equivalent exponential form quick. So the base of the log is always the base of the exponent. So log base 7 is saying 7 to the power of something. Solution is our power, so the 3 is 7 to the third equals x. The second one here, 4 to the power of x equals 256. And our third one, x to the power of 6 equals 15,625. Any questions on those? So now let's go the other direction. If I give you the exponential, we need to be able to find the appropriate logarithmic form. So I might have 4 to the power of 5 equals 1,024. Well, the base of the log became the base of the exponential. The opposite is true as well. The base of the exponential is the base of the log. This is the log base 4. The power, the result of the log was the power, so the power becomes the result of the log. And the result of the exponential was the object of the log. So that goes back in there. So if I have 3 to the power of x equals 81, that's saying log base 3. The solution here is the object of the log is of 81 equals, the solution of the log is the power of the exponential, equals x. I'm going to have you try a few in your notes here. So let's have 5 to the power of 3 equals x. 7 to the power of x equals 2,401. And x to the power of 6 equals 64. Turn those into their equivalent logarithmic form. So the base of the exponential becomes the base of the log. So this is a log base 5. The object of the log is the solution from the exponential, so x is the object. The power of the exponential is the solution of the log. That's log base 5 of x equals 3. The second one, that's log base 7 of 2,401 equals x. And finally, the last one, that's a log base x of 64 equals 6. Now, as I look at each of these, the question becomes, is it beneficial to change them into an exponential? Take them one at a time. This first one here, is it beneficial to make it an exponential? No, it's not. I mean, that truly is the correct exponential or the logarithmic form for it, but changing that exponential form to a logarithmic form doesn't do anything for us. In the exponential form, 5 to the power of 3 is 125. So all I have to do is do the power and I've solved that equation. So the logarithmic form doesn't help me there at all. This last one down here, the variable is the base of the log. That doesn't help us at all either. X to the 6th equals 64. If I was going to try to solve that, the form that would be beneficial is a radical form, a root. The 6th root of 64 equals x. That's the form that would make that most beneficial for us. The only form where it's beneficial to change that exponential to logarithmic is when the variable is in the power of that exponential form. So as we're exploring these logarithms, let's talk a little bit about the base of the log. That base b has some restrictions. First of all, let's look what would happen if b equals 0. If b were 0, log base 0 of x equals y would convert to 0 to the power of y equals x. While this is true, it's very useless because the only possible value for x here is 0, because 0 to the power of anything is going to be 0. So if b equals 0, the logarithm really doesn't do anything. It's redundant. It's just saying 0 equals 0. It doesn't matter what value y is because x must be 0, and 0 to any power is going to give us 0. So we do not allow, in a logarithm, we don't allow the base of the log to be 0. All right, a little more, so just use one slash, is a little clearer, so it doesn't look like a pound sign. So b can't be 0. Another case we want to look at is what if b is 1? Well, we have log base 1 of x equals y. Gives us the equivalent exponential of 1 to the power of y equals x. Well, here again, there's only one possible value x can take on. Here, x must equal 1. Because no matter what that value of y is, 1 to any power is going to be 1. There's no other possible solution for it. So we say that b cannot equal 1. What if b were negative? Let's just try negative 1. We would have log of negative base negative 1 of x equals y. That's saying negative 1 to the power of y equals x. Well, negative 1 to any power is either going to be positive 1 or negative 1. I can't take negative 1 to a decimal power, so it has to be an integer power. Negative 1 to the power of 5 is going to be a negative 1. Negative 1 to the power of 4 is a positive 1. So there would only be two possible values there. Y would either have to be 1 or negative 1, and it would be indeterminate because x could be, if y is 1, x could be any even number. If y is 2, if x has to be 1 or negative 1, and y could be any even number if x is positive 1. If x is negative 1, y could be any odd number. It's indeterminate, can't be solved. In fact, b for any negative value of b, we run into similar issues. We can't have decimal values, decimal powers, because you can't take a root, an even root at least, of a negative number. So we do not allow b to be less than 0. Can't be a negative. So b has to be greater than 0. So those are our restrictions on b. b must be positive, but it can't equal 1. But b can take on values between 0 and 1. So let's take a look at what happens when b takes on those values. Log base 1/2 of 1/8 equals x. That's saying 1/2 to the power of x equals 1/8. Now it might take a little work, but with a little inspection, you can see here 1/2 to the power of 3 equals 1/8. So x must equal 3. If we have a fractional base or a decimal base, does that mean we can only have results here that are fractions or decimals? Certainly not. Let's stick with that base of 1/2. What if this is a 4? Well, this is saying 1/2 to the power of x, oops, not 1/4, 1/2. The power of x equals 4. It is possible. 1/2 to the power of -2 equals 4. Show you on the calculator. 1/2 to the power of -2 gives us a positive 4. Remember that negative power is a reciprocal, so 1/2 the power of -2 is equivalent to 2 to the power, the reciprocal of 1/2, which is 2, to the positive power. Likewise, let's do a log base 5 of 1/25 equals x. That's asking 5 to what power? 5 to the power of x equals 120, or equals 1 over 25. Well, I can rewrite 1 over 25 as 1 over 5 squared. 1 over 5 squared being a reciprocal, that's equivalent to 5 to the power of negative 2. So we have 5 to the x must equal 5 to the negative 2. X must equal negative 2. Similar here, log base 2 of 1 over 64 equals x. That is saying 2 to what power equals 1 over 64? I can write 64 as a power of 2. 64 is 2 to the power of 6, so that's 1 over 2 to the 6th. Well, 2 to the 6th is a reciprocal. 1 over 2 to the 6th is a reciprocal. That's 2 to the power of negative 6. So if 2 to the x equals 2 to the negative 6, x has to equal negative 6. We also bring back in the letter E from Monday's class. E, if you recall, is that natural constant. 2.71, whatever, as it keeps going. That's our continuous growth factor in nature, or continuous decay factor. Because there are a number of exponentials that are of the form e to a power, we have a log base e. So log base e of y, of x equals y, is saying e to the power of y has to equal x. This occurs enough in algebra and math, log base e, that we have defined a special function for it. Rather than doing log base e, we abbreviate that natural log as ln. So anytime you see ln of x, what that is saying is log base e of x. ln technically stands for log-based natural constant. That's where ln comes into it instead of nl. So if I want to solve some simple logarithmic equations, log base 3 of x equals 5. Sometimes it's helpful, as we saw before, sometimes it's helpful to change it to exponential. Sometimes it's just as helpful to leave it like this. This one, if I change it to its equivalent exponential, that's 3 to the 5, the 5th power equals x. And that's pretty simple. 3 to the 5th power is 243. So x is 243. I might have log base x of 64 equals 6. That's saying x to the power of 6 equals 64. It was beneficial to convert it into an exponential. Even though we're not going to use the power to solve it, we're actually going to use a root. This is going to do a 6th root to reverse that power of 6 to get x by itself, giving us x equals 2, or we have to be careful, 2 or negative 2. 2 to the 6th equals 64, but negative 2 to the 6th power would also equal 64 because it's that even root. We have to look for that second solution. Log base 2 of 8 equals x. This is saying 2 to the power of x equals 8. We have to solve this like we did some at the beginning of the hour. We have to turn 8 into an exponent with a base of 2. Well, 8 is 2 to the power of 3. So x equals 3. Log base 7 of 1 equals x. This is saying 7, the power of x equals 1. This one's kind of a gimmick. Since the variable is in the power of the exponent, the only way so far that we know how to solve them is to make this an equivalent exponent with a base of 7, with the same base. Right, so how can I write 1 as in something to a power other than 1? Well, remember, anything to the power of 0 equals 1. That is 7 to the power of 0. So if 7 to the x equals 7 to the 0, x equals 0. And we've seen similar to this, log base 3 of 1 over 81 equals x. That's saying 3 to the power of x equals 1 over 81. Again, the x is in the power of the exponent, so we have to write the other side as an exponent with a common base, with a base of 3. 81 is 3 to the power of 4, so 1 over 81 is 1 over 3 to the 4th. 1 over 3 to the 4th is equivalent to 3 to the negative 4th. So now because we have exponentials with both have the base of 3, powers have to be equal. So x equals negative 4. We might have log base 6 of x equals negative 3. That's saying 6 to the power of negative 3 equals x. So all we have to do there is do the power. 6 to the power of negative 3 is 1 over 6 to the 3rd. 6 times 6 times 6 is 216. So x equals 1 over 216. Okay, I'm actually a couple of minutes late for our break, so let's go ahead and take our break here. And let's try to get back at 10:30. We'll start more new material. So we have said that the logarithm and the exponential are inverses of each other. If you recall, other inverses, if we used them together, they canceled each other out. Like x plus 5 minus 5 just gave us x. Or x times 3 and then divided by 3 gave us x. And we could go the opposite order. X minus 5 and then plus 5. Still got us back to x. X divided by 3 and then times 3 still gets us back to x. On a more complex scale, x to the 5th and then take the 5th root of that gives us back x. Again, in the opposite order, same is true. If I take the 5th root of x, oops, wrong spot. the fifth root of x, and I take that to the power of 5, the fifth root and the fifth power cancel out, and we get x, no matter what order they're taken in. The same is true for our logarithms. Because a log of a certain base and an exponential of a certain base cancel each other out, they're inverses, they will cancel each other out. So log base 5 of 5 to the power of x, the log base 5 and the 5 to the power of cancel out, that leaves us with just x. Or likewise, we might have 8 to the power of log base 8 of x. The 8 to the power of and the log base 8, once again, cancel out. That leaves us with just x. The final situation we can run into is the log of base anything. I'll just put the variable y in here of 1. Remember that saying is what to, see that equals x. Y to the value of x equals 1. Well, it doesn't matter what the value of y is. If that result is 1, x has to equal 0. Because anything to the power of 0 equals 1. So if the object of the log is 1, the result is always 0. These inverse relationships will come in handy later on as we start to solve exponential and logarithmic equations. For now, let's look at graphing a log. So graphing logarithmic functions. These are inverses. Remember, an inverse, we look at inverse functions from last section, last unit. The graph was reflected around the line y equals x. Similar thing happens with logarithmic functions. So the logarithm is an inverse of an exponential, and an exponential, the graph of an exponential function, looked either like this or like this. The graph of a logarithmic function is going to be reflected around that line y equals x. So it's going to look like that or like that. So let's take a peek at how that works. Notice x cannot have values less than 0. So we're going to graph f of x equals log, I'm going to keep it simple, base 2 of x. So I'm going to have values of x and values of y. Since 2 is positive, x cannot be negative. Because 2 being positive, there is no power I can take it to give me a negative number. So no matter what power I put in here on the 2, my result's always going to be positive because 2 is positive. In fact, x can never be 0 because the only way the x could be 0 is if the base of the log were 0. So x has to be larger than 0. So I'm going to start out with x being 1/4. So now remember what this is asking. I'm going to redo my equation here. What this is asking is 2 to the power of y equals x. So 2 to what power equals 1/4? Excuse me. That power would be a -2. So if x is 1/4, y is -2. So 1/4 -2 is right in there. Now I chose the 1/4 because I knew 4 was a power of 2. So I'm going to choose 1/2 because I know 2 is also a power of 2. 1/2 is 2 to the power of -1. So if x is 1/2, y is -1. This next one's always kind of a give me. If x is 1, y has to be 0 because it takes something to the power of 0 to give me 1. So x is 1, y is 0. If x is 2, well, 2 to the power of 1 is 2. So that gives me the ordered pair of 2, 1. The next value I'm going to choose for x, because I know it needs to be a power of 2 to make this simple, is going to be 4. Y to the power of, or 2 to the power of 2 equals 4. So if x is 4, y has to be 2. So that's giving me a point over here at 4, 2. And at this point, I've probably got a pretty good idea what shape my graph is going to be. It's going to be the curve looking like this. As long as that base of the logarithm is bigger than 1. That b is bigger than 1. We're going to get a curve like that. Just like with our exponentials, the only way to make that curve go the other direction is if we have a base between 0 and 1. Log base 1/2 of x. Well, what happens here is our solutions basically flip around. I'm going to choose values of 1/4, 1/2, 1, 2, and 4 for x again. If x is 1/2, this is asking us 1/2 to the power of y equals x. Well, if x is 1/4, 1/2 to the power of 2 equals 1/4. If x equals 1/2, 1/2 to the power of 1 equals 1/2. If x equals 1, well, anything to the power of 0 gives us 1, so y is 0. To be 2, 1/2 to the power of -1 gives us 2. 2 is the reciprocal of 1/2, so -1, the power of -1 gives us the reciprocal. And if x is 4, y has to be -2. So that gives us the points here at 1/4, we're at 2. 1/2, we're at 1. 1, we're at 0. 2, we're at -1. And 4, we're at -2. So notice the curve goes the opposite direction. Just like what we did with our exponential graphs, we can move these around. First, you'll notice this has a vertical asymptote at the y-axis, or x equals 0. And now our crossing point, or one of our constant points, is on the x-axis. It crosses the x-axis at 1. So as we multiply or divide it, it's going to move that starting point. So I might have y equals log base 2 of x minus 2 and then plus 3. What's that going to do to our graph? Well, what it's going to do, first of all, our vertical asymptote's not going to be at x equals 0 anymore. It's going to be at x equals 2. I didn't multiply by anything up here, so we're going to still cross 1 unit away from that, but that axis that we cross is not going to be the x-axis anymore. This plus 3 means we've moved up 3 from that x-axis. So that's what we're going to be looking at going through. We're going to cross that 1 unit away from our vertical asymptote. And since it's log base 2, we're going to have a curve that looks like that. In these functions, the domain. Remember, in our exponential functions, the domain was from negative infinity to a positive infinity. We could put any value in those for x that we wanted to. Here, that's not true. Our domain is for values of x that are greater than that vertical asymptote. The range, however, now can go from negative infinity to positive infinity. So if I give you a function here, f of x equals log base 5 of x plus 3 plus 1. On our graph, remember this plus 3 to the x means we're moving the opposite direction, negative 3. So our vertical asymptote moves from x equals 0 to x equals negative 3. So what that means is our domain is going to go from negative 3 to positive infinity. The range is always on a logarithmic function, unless it's a rational logarithmic function. We're not going to throw in fractions in those in the general functions right now. Is just going to go from negative infinity to positive infinity. If I look at a simpler logarithmic function, f of x equals the log base 7 of x. Since there's nothing added or subtracted to the x, nothing shifting that horizontal axis for us, or that vertical axis for us, I should say. The domain of that is going to be the standard domain for a logarithmic function, 0 to infinity. The range as always with a logarithmic function, from negative infinity to positive infinity. Now, because of the close relationship between powers, exponents, and logarithms, there are some properties of exponents that carry over into logarithms. If I have x to the power of a times x to the power of b, that becomes x to the power of a plus b. The logarithmic equivalent of that, splitting it back up, if I have log of a times b, I can separate that. Remember, this is just saying x to the power of equals a. I can separate that into log of a plus log of b. So for an example, I can take something like log of 40. I can separate that into log of 4 times 10. And then I can further separate that as log of 4 plus log of 10. Why would I want to be able to do that? Well, because sometimes there are certain logs that are easy to calculate. Now, remember what we said, log for exponentials, that 10 to the power of is common. If I don't write an index on my logs here, that is assumed to be a log base 10. On your calculator, there is a log key. You can see right here, log. That log key is a base of 10. It's not written there, but that's a log base 10. You can see there's an ln key, that's a log base e. All other bases of logs we're going to have to work with differently, try to calculate them. We'll look at something called the change of base formula in a little bit before we're done today. Now, if I wanted, let's assume this is a log base 10. Let's just double check that. Let's do the log of 40, giving us 1.602. Let's compare that to the log of 4. Log of 4 should be 0.602. In the log of 10, I can punch it in the calculator, but I don't need to. Log of 10 is just 1. 10 to the power of 1 is 10. That adds up to 1.602. So that holds true. It works out. Just like with our exponents, x to the a divided by x to the b is x to the power of a minus b. If I have log of a divided by b, I can break that down into log of a minus log of b. And if I have log of a to the power of b, or sorry, x to the power of a to the power of b, that's x to the power of a times b. This one's a little bit harder to recognize, but if I have log of a to the power of b, that's equivalent to b times the log of a. Let's do an example of that. So let's do log of 125. That's equivalent to log of 5 to the third power. 125 is 5 to the third power. which is, according to this, equivalent to 3 times the log of 5. Let's take a look at that. Let's calculate the log of 125, giving us 2.097. Over here, it's 3 times. Let's calculate the log of 5, which is going to be 0.699. If we multiply that out, we do get 2.097. So these rules for logs allow us to take different logs and split them up. So if I have log of x squared over x minus 7, first thing I can split up here, I can't do anything with this x squared until I have it by itself. I can't take that power out until I got it by itself. I'm going to split up the division. Remember, a log of a divided by b is log of a minus log of b. That's going to be log of x squared minus log of x minus 7. Now, log of x minus 7 is subtracted. We can't break that up. We can only break up multiplication, division, and powers. Log of x squared, however, we can simplify that. X squared, we're going to take the 2 out front of the log. Log of x squared is 2 times log of x. And of course, the log of x minus 7 doesn't change. So log of x squared over x minus 7 is equivalent to 2 times the log of x minus the log of x minus 7. Similar to that, log of 4x over 2 minus x squared. Well, again, we're starting off with the division, so we're going to split that up. So that's log of 4x minus log of 2 minus x squared. Log of 4x is log of 4 times x. So we can split that multiplication up into log of 4 plus log of x. This piece here, we're really tempted looking at that x squared to try to pull that 2 out of there. But it's not x squared by itself. It's 2 minus x squared. We cannot split up subtraction. So unfortunately, there's nothing we can do with that. That just stays log of 2 minus x squared. If we had log of x squared minus 4 over 3x to the third plus 24x squared plus 48. We can, of course, split that into log of x squared minus 4 minus log of 3x to the third plus 24x squared plus 48. But these polynomials inside the logs are factorable. X squared minus 4 can be factored into x plus 2 times x minus 2. We'll split that up in a minute. Over here, log of the 3x to the third, 24x squared plus 48. First thing I can do there, I'm going to do this in kind of steps here. I can factor out the 3x. If I take out a greatest common factor of 3x, I'm left with x squared plus 8x plus 16. x squared plus 8x plus 16 is a perfect square trinomial. So this is 3x times x squared plus 8x plus 16 is x plus 4 squared. So now I've got a lot I can do here. I can split this up into log of x plus 2 plus log of x minus 2. Over here, I have to be careful now. There is a minus in front of this. So I have to make sure that no matter what I do with this, I distribute that negative. So I'm going to write this as negative times, I'm splitting the log of 3x plus, because this is multiplied by the x plus 4 squared. I'm going to pull the squared out to make that 2 times the log of x plus 4. I wrote that in a different color because we still have to do a little bit of algebra here. This minus in front of that has to be distributed. So the beginning piece here, log of x plus 2 plus log of x minus 2, that's not going to change. But when we distribute that negative, that'll be minus log of 3x. And then minus 2 times the log of x plus 4. That's as far as we can break that down. We can use these rules of exponents to recombine things. If I have, log of x minus 2 plus log of 3, I can recombine those to be log of x minus 2 times 3. And of course, I can multiply those out, distributing the 3 back through the parentheses, log of 3x minus 6. Or I might have 2 times the log of x plus log of 5. Well, 2 times log of x, that is log of x squared. Log of x squared plus log of 5, that's log of x squared times 5, or 5x squared. I can multiply them back together. In your notes, I'm going to give you a couple minutes here. I want you to recombine number 1 here, 4 times the log of x plus 2 times the log of y. The second one I want you to combine is just log of 5 minus log of x. I'll give you a minute to recombine those, and we'll go over them. So for the first one, 4 log of x, that's log of x to the fourth. 2 log of y, that's log of y squared. Plus means I'm going to multiply them, so that's log of x to the fourth y squared. The minus is division, so log of 5 minus log of x is log of 5 divided by x. If I try to split them up, let's try something like log of 5 divided by x squared. And then let's do log of 3x to the fourth. Split those up for me. So 5 over x squared, so that's going to be log of 5 minus log of x squared. Then we'll split up the x squared. This will be log of 5 minus 2 times the log of x. Over here, log of 3 x to the fourth. That'll be log of 3 plus log of x to the fourth. We split up the multiplication to first. So then log of 3 won't change, but x to the fourth will be 4 log of x. The final equivalency we have is our change of base formula. We already mentioned the calculator only has 2 logs, log base 10 and log base e. Unlike our radicals, most calculators don't have a log base x function where you can put in your own base. I always thought that was weird, but the change of base formula makes it unnecessary to do that. What the change of base tells us is if we were trying to do a log base b or base a of b, that is equivalent to log of any base of b divided by the log of that same base of a. So if I'm trying to find log base 4 of, let's do 256. Log base 4 of 256 should be 4. Oops, I wrote 254 when I said 256. So that's going to be log of, the object is the 256 over log of the index of 4. It does not matter on our calculator whether we use the log key, the log base 10, or if we use the ln key, the log base e. Let's do it both ways. Now we do have to make sure we use our parentheses properly. So log 256, close the parentheses, divided by log of 4. We don't have to close this one, but we're going to just to be complete. Gives us 4. Notice if we used ln of 256, close the parentheses, divided by ln of 4, close them up again. also gives us 4. 4 to the power of 4 equals 256. So log base 4 of 256 is 4. If I try to calculate log base 5 of 15,625. So again, I'm going to use a log 15,625 over log of 5. Now 5 to the power of 6 is 15,625. So again, log 15,625, make sure I close that parentheses, divided by a log of 5, we get 6. If I use the ln instead of the log key, log base e instead of log base 10, log 15,625, close the parentheses, divided by log of 5. Oops, I gotta make sure I use the same one. Gotta use ln here. ln of 5. Notice I still get 6. So I can use any log to calculate any other log base as long as I use that change of base formula. So in your calculators, if you have them available, I want to calculate for me log base 2 of 1024. Did you get 10? Perfect. Log base 2 of 1024 is 10. So some applications to wrap us up here. One of the biggest applications that I know of for logarithms is electrical power. And by electrical power, I'm not talking about electricity. Just bare electricity. Bare electrical power as far as your light bulbs and your appliances is just your voltage times your current. I am talking about the power of an electrical device, whether it's an amplifier, a television, cable TV receiver, whatever. I'm talking about something that's receiving a signal. So it's a signal strength type power. The power in decibels the bell is a unit of power named after Alexander Graham Bell, is equal to 10 times the log of an output voltage compared to 1 millivolt. So if I have a device that is putting out 4 millivolts, the power is 10 times the log of 4 millivolts divided by 1. Now the millivolts divide out, so it's just 4 divided by 1, or 4. So 10 times, and this is a log base 10 of 4, giving us 6.02 decibels. About 5 minutes. If I increase that signal strength, this is one of the reasons why the logarithmic scales are so useful. If I increase that signal strength from 4 to 8 millivolts, I've doubled the signal strength. It's now 10 times the log of 8 over 1, or 10 times log of 8. I get 9.03 decibels. So when I went from 4 to 8, I went from 6.02 to 9.03. If I increase that output voltage again to 16, now I have doubled it again. 10 times the log of 16 over 1. If I calculate that, I'm going to get 12.04 dB. On a logarithmic scale like this, a logarithmic function, when you double that input, the x value in this case, we doubled from 4 to 8, it went up by 3.01, from 6.02 to 9.03. Every time I double it, from 8 to 16, it goes up by another 3.01 to 12.04. If I doubled that output voltage again to 32 millivolts, I can calculate it out, but I don't have to. It's going to go up by another 3.01. This is going to be 15.05 dB. Another application that we run into is temperature increase in an enclosed vehicle over time. Our function of temperature, and I'm throwing in numbers here that are the 13.4 and the 11.6 are dependent upon the initial temperature within the vehicle and the temperature outside of the vehicle and the thermal properties of the vehicle itself. But this equation is a common equation used for describing temperature change. If we let x, or we could have used t for time, be 6 minutes. We'll put that in there. This will be 13.4 times ln of 6 minus 11.6. So 13.4. No, we have to use the ln key. So I do times, I have to use the ln key. 6. Be sure to close our parentheses. Minus 11.6. We get 12.41 degrees. And that is true in a hot sun. In 6 minutes, a vehicle can go up by 12 degrees at a time in just a 6-minute span. Okay, so we do have homework from last class, from Monday, that is due tomorrow. Call that an old homework. It'll be due Thursday. And based off that homework, there's a quiz that is due Friday. So that homework is off the lecture from Monday and or the quiz is off the lecture from Monday and last Thursday. Then there's a new homework for today that'll be due next Tuesday. I guess I forgot to ask, were there any questions on the homework from last Monday that you wanted me to go over? We're good? Okay, well, with that, you guys have a great day, have a great weekend, and we'll see you on Monday.